For billions of years, diamonds have been locked away beneath the Earth's surface, ancient, unyielding, and dazzling. Formed deep within the mantle under crushing pressure and unimaginable heat, or born in the hearts of dying stars and scattered across space, they've become symbols of beauty, power, and permanence. But today, diamonds are at the center of a new story, one not about luxury, but about technology. Imagine a material so hard it can cut through anything, so thermally conductive it outperforms metals, and in some cases even able to conduct electricity. Now imagine that same material not as a rare gemstone, but as something we can make, in any shape, in any size, inside a laboratory. This is the beginning of what scientists are calling the new diamond age. The transformation began with a single question. Could science build a better diamond than nature itself? Natural diamonds are remarkable, but they have flaws. They crack under extreme pressure, they're expensive to obtain, and only the rarest blue diamonds, like the legendary Hope Diamond, possess the ability to conduct electricity. If researchers could engineer diamonds with perfect properties, the implications would be staggering. Electronics, spacecraft, medicine, energy systems, all could be revolutionized. The race began in the mid-20th century. In secret labs, scientists at General Electric tried to replicate the intense conditions found 150 kilometers underground. After years of experimentation, they succeeded. For the first time, synthetic diamonds, small, tough, and industrially useful, were born. Over time, technology advanced. New methods like chemical vapor deposition allowed researchers to grow diamonds inside vacuum chambers, atom by atom. What nature achieved over billions of years, scientists could now do in a matter of days. Then came a cosmic twist. Scattered across parts of South America and Central Africa, scientists discovered strange black diamonds, carbonado. Unlike normal diamonds, these were riddled with tiny voids and made up of millions of interlocking crystals. They didn't form inside Earth. Evidence suggested they originated in supernova explosions, glued together in the vacuum of space and delivered to Earth by meteorites. Their unique structure held a crucial secret. It's possible to create diamonds at low pressure, a breakthrough that would change everything. Today, researchers are harnessing that knowledge to craft super diamonds, materials tougher than anything found in nature, designed specifically for high-tech applications. These diamonds conduct heat 5 times faster than copper. They can carry 30 times more power than silicon and withstand temperatures that would destroy conventional electronics. They're being shaped into wafers for microchips, lenses for spacecraft, and even nanoscopic resonators that vibrate 100 billion times per second. Diamonds, once prized only for their beauty, are becoming the building blocks of the future. They promise faster computers, cooler electronics, stronger spacecraft, and scientific instruments capable of reaching new extremes. But this transformation raises a profound question. Are we simply copying nature's work, or are we beginning to surpass it? This is the story of how humanity learned to forge its own stars, to recreate one of the universe's rarest materials, and to unlock its hidden powers. This is the story of the rise of the super diamond. Part 1: The First Clues. A spark from the past. It began, like many technological revolutions, with a problem. In the middle of the 20th century, engineers were facing a looming wall. The world was rapidly electrifying. Power grids were expanding, computers were beginning their march into industry, and the demand for faster, more efficient electronics was growing at an unprecedented pace. Silicon, the foundation of modern semiconductors, had carried humanity from vacuum tubes to microchips. But as systems grew more complex, one flaw became impossible to ignore: heat. Silicon's ability to transmit electricity is excellent, but its tolerance for heat is not. Once temperatures pass around 300 degrees Fahrenheit, silicon-based electronics begin to falter. Circuits slow down, devices overheat, and failure rates skyrocket. The more power you push through silicon, the more heat it generates. And the hotter it gets, the less reliable it becomes. Engineers were designing elaborate cooling systems just to keep silicon from melting down. They could see the ceiling approaching. While industries struggled with this limitation, a very different kind of discovery was quietly being made in the realm of mineralogy. At the Smithsonian Institution in Washington, D.C., researchers were studying a famous gemstone under ultraviolet light. The object of fascination was the Hope Diamond, a deep blue, 45.52-carat jewel that had captivated imaginations for centuries. Legends claimed it was cursed, stolen from a sacred Indian temple, and that its blood-red glow under ultraviolet light was proof of supernatural power. But scientists weren't interested in curses. They were interested in why the diamond glowed. When the ultraviolet lights were switched off, the Hope Diamond emitted an intense orange-red phosphorescence that lingered in the darkness. Using spectrometers, researchers broke down the glow into its component wavelengths. The mystery unraveled not through myth, but through chemistry. Two trace elements, boron and nitrogen, were responsible. Boron produced a blue hue. Boron combined with nitrogen emitted the haunting red light. This discovery was more than a curiosity. Boron atoms were found to give blue diamonds a completely different electrical behavior from their colorless counterparts. Pure white diamonds, composed entirely of carbon, are excellent insulators. Pass a current through them and nothing happens. But when boron is present, even in minute quantities, the diamond becomes a semiconductor, able to conduct electricity like silicon does. This was the spark, a naturally occurring material that could both conduct electricity and dissipate heat far more efficiently than silicon. The Hope Diamond wasn't just beautiful, it was technologically significant. The material beyond silicon. As researchers dug deeper, they found that all diamonds, not just blue ones, possessed another astonishing property: unmatched thermal conductivity. Heat moves through diamond 5 times faster than through copper. It doesn't just tolerate extreme temperatures. It thrives in them. A diamond chip could carry 30 times more power than silicon while remaining stable. Theoretically, a computer built on diamond semiconductors could run at speeds that would melt any silicon chip within seconds. The catch was obvious. Diamonds like the Hope were incredibly rare. Blue, boron-rich diamonds represent less than 1 in 100,000 natural stones. They come in irregular shapes, unsuitable for industrial use. And even if they could be used, mining enough to build a modern semiconductor industry was unthinkable. The only path forward was to build them ourselves. Project Superpressure in 1950, a small team at General Electric decided to try something radical. Led by scientist Tracy Hall, they launched Project Superpressure, a covert program to replicate the natural formation of diamonds inside a laboratory. Nature's recipe was clear but brutal. 150 kilometers underground, carbon is subjected to pressures 50,000 times greater than atmospheric and temperatures surpassing 2,700 degrees Fahrenheit. Over millions of years, those conditions turned simple carbon into crystal lattices harder than anything else on Earth. G's challenge was to compress that geologic timescale into a human one. They built enormous hydraulic presses capable of exerting 800,000 pounds of pressure per square inch. They heated graphite, the purest form of carbon, past 2,500 degrees Fahrenheit. And they waited. Year after year, experiment after experiment, the project burned through millions of dollars and countless failures. But in February 1955, the impossible happened. Inside one of their presses, under brutal force and searing heat, carbon transformed. The world's first synthetic diamond had been created. These early diamonds weren't clear, flawless gemstones. They were small, gritty, and perfect for cutting tools. But their industrial impact was immediate. Diamond-tipped drills cut through granite like butter. Oil companies drilled deeper, faster. Manufacturing changed overnight. For the first time, diamonds had left the realm of luxury and entered the world of machines. Yet, as revolutionary as this was, it still wasn't enough. These synthetic diamonds were too small for electronics. Their structure was closer to natural industrial diamonds than to the rare blue semiconductors like the Hope. GE had proved we could make diamonds, but not yet the kind that would power a technological revolution. Whispers of a bigger idea throughout the late 20th century, researchers around the world began experimenting with alternative methods. What if, instead of brute-forcing nature's pressure, they could grow diamonds in a more controlled way? What if size, shape, and even electrical properties could be engineered deliberately? The idea seemed far-fetched until a strange clue arrived from outer space. Scattered across parts of South America and Central Africa were black, porous stones that didn't match any known geological formation. They were called carbonado. Unlike ordinary diamonds, carbonado was not a single crystal. It was composed of millions of interlocking microcrystals, fused together in a way that made it not only larger but tougher than conventional diamonds. Microscopic analysis revealed tiny voids inside, something impossible for diamonds formed deep within Earth's mantle. The leading theory was astonishing. Carbonado formed in the vacuum of space. As supernovae exploded, they created countless tiny diamonds. In the weightless void, these particles collided, fused, and were eventually delivered to Earth by meteorites. The implication was profound. If diamonds could form under low pressure in space, maybe they could be grown under low pressure in a lab. For decades, this was nothing more than a hypothesis, a scientific curiosity. But soon, it would become the foundation of a new technology. Part 2. Breaking the limits. The first synthetic revolution by the time the 20th century approached its second half. The creation of synthetic diamonds was no longer science fiction. It was an industrial reality. Project Superpressure had proved that humans could compress carbon into diamond. But while the world marveled at GE's achievement, within scientific circles, another, quieter revolution was beginning to take shape. The question was no longer, can we make diamonds? It had become, can we make better ones? Industrial diamonds, powerful but limited. The synthetic diamonds produced in the 1950s were transformative for heavy industry. These small, hard crystals were ideal for cutting, drilling, and grinding. Diamond-tip tools dramatically improved the efficiency of mining and manufacturing. Oil companies used diamond drill bits to bore deeper into granite formations, reaching reserves that had previously been inaccessible. In laboratories and factories around the world, banks of high-pressure presses worked day and night, producing industrial diamonds on a massive scale. By the 1970s, South Africa's Element 6, a De Beers subsidiary, became a global leader in synthetic diamond production, refining GE's methods and increasing output. But the diamonds they produced had two key limitations. First, they were too small, typically a few millimeters across, far below the size needed for advanced electronics or optical applications. Second, their internal structure was not engineered. They were mostly copies of natural diamonds. Strong, yes, but electrically inert. They couldn't carry current like the rare boron-rich blues. The diamond had proven its industrial might, but its true technological potential remained locked away. The search for control throughout the 1980s and 1990s, scientists began to think differently. Instead of mimicking the crushing forces of the Earth's mantle, what if they could control how a diamond grew, atom by atom? This shift in thinking led to the development of a technique that would redefine diamond science: chemical vapor deposition, or CVD. Instead of relying on immense pressure, CVD uses a vacuum chamber and carefully controlled gases to encourage carbon atoms to assemble themselves into diamond structures. The process starts with a tiny diamond seed, often no bigger than a grain of sand. The seed is placed inside a vacuum chamber heated to over 3,600 degrees Fahrenheit, just below atmospheric pressure. Methane, a carbon-rich gas, is pumped in, followed by hydrogen. Then, microwave radiation bombards the gases, causing them to break apart. Carbon atoms are liberated and, in this energetic environment, they settle on the seed's surface, locking into the familiar tetrahedral lattice of diamond. Layer by layer, the diamond grows. What nature accomplishes in billions of years, scientists can now replicate in days. This was more than just a clever trick. It was a paradigm shift. With CVD, researchers were no longer prisoners of size, shape, or even time. They could, in theory, grow any form of diamond they wanted, from thin wafers to large single crystals. And because the process operated at relatively low pressures, it opened doors that brute force synthesis never could. Space stones and new insights while CVD was being perfected on Earth. Evidence from the cosmos continued to influence the field. Carbonado, those mysterious black diamonds from space, provided a crucial insight. Diamonds didn't have to be formed under extreme pressure. Their structure, composed of millions of interlinked crystals riddled with voids, suggested that diamonds could assemble under low pressure if the environment was right. This was precisely what CVD provided. A low-pressure environment, a source of carbon, and enough energy to force atoms into alignment. By imitating the vacuum conditions of space, scientists were, in a sense, replicating the supernova forge on their laboratory benches. The implications were enormous. Suddenly, diamond growth was not restricted to the constraints of Earth's geology. The laboratory had become its own planet, its own star. Genesis and the race to scale. One company in Florida, Genesis, took this idea further than anyone else at the time. By the late 1990s, Genesis was using a combination of high-pressure seeding and CVD-like conditions to grow large gem-quality diamonds. Not in millions of years, but in 4 days. The process began with a tiny diamond seed, either natural or artificial, placed next to a source of graphite. The chamber was heated and compressed, and as the graphite broke down into carbon atoms, those atoms migrated and crystallized on the seed. Molecule by molecule, the diamond expanded. The result was remarkable. Genesis could grow stones up to 3 times larger than the original seed. These diamonds weren't just industrial grit. They were large, clear crystals suitable for cutting into gemstones, or for something far more ambitious, technology. The ability to grow large diamonds on demand hinted at a future where diamonds could be designed, not merely found. The rise of the diamond wafer. Meanwhile, at the U.S. Naval Research Laboratory in Washington, D.C., a different experiment was underway. Instead of growing large single gems, researchers began sprinkling tiny diamond seeds across silicon wafers, like scattering grains of salt on a table. Then they placed these seeded wafers into CVD chambers. As the carbon atoms settled and crystallized, each tiny seed expanded until they touched and fused with their neighbors, forming a thin, continuous sheet of diamond. The result was a diamond wafer, less than 1/50th of an inch thick but up to 8 inches wide. These wafers could be shaped to match standard semiconductor formats, effectively replicating silicon chips but with properties far beyond what silicon could offer. They were harder, more heat-resistant, and electrically tunable through doping with boron. Suddenly, the concept of diamond-based microelectronics was no longer speculative. It was a matter of engineering refinement. A new material class emerges. By the early 2000s. The world of material science was buzzing. Diamond, once seen only as a luxury gemstone or a tool for drilling, was being reborn as a functional material. It wasn't just one property that made it valuable. It was the combination. Extreme hardness, record-breaking thermal conductivity, tunable electrical properties through boron doping, optical clarity across ultraviolet to infrared spectra. Together, these characteristics defined an entirely new class of material, the superdiamond. Unlike natural stones, superdiamonds could be engineered, shaped, grown, and optimized for specific industrial and technological uses. The breakthroughs of the late 20th century laid the foundation. But the next step would be even more dramatic. Scientists were about to push diamond technology beyond what anyone thought possible. Not just matching nature, but surpassing it. Part 3. Engineering the impossible. Building the superdiamond. By the dawn of the 21st century, the world's laboratories had accomplished something astonishing. Diamonds could be made in a matter of days, shaped into wafers, and engineered with extraordinary precision. But scientists were not satisfied. They didn't just want to replicate nature, they wanted to surpass it. The goal was ambitious. Create a superdiamond that combined every extraordinary property of natural stones: hardness, thermal conductivity, electrical tunability, optical clarity, but in shapes and sizes nature could never produce. This meant building crystals larger than anything mined, tougher than any gemstone, and flexible enough to be adapted for next-generation electronics, aerospace, and high-pressure science. The natural blueprint versus human ambition. In nature, diamond formation is dictated by geology. Carbon atoms are forced into a tetrahedral lattice deep in the Earth's mantle, under conditions so extreme they are difficult to imagine. Temperatures must exceed 1,500 degrees Celsius. Pressures reach more than 50 kilobars, the equivalent of 4,000 grown men standing on your foot. Even then, the diamonds that emerge are far from perfect. They contain inclusions, dislocations, and impurities, and most are small. The rare exceptions, like the Hope Diamond, are geological accidents, anomalies created by unique combinations of pressure, temperature, and trace elements. For industrial and technological use, relying on such accidents was not an option. So scientists began to reverse engineer the process. If they understood every variable of diamond formation, from atomic bonding to lattice growth dynamics, perhaps they could guide the process to create flawless, custom-shaped crystals. Chemical vapor deposition reimagined the key lay in refining chemical vapor deposition. Early CVD experiments proved the concept but were slow and prone to structural imperfections. Researchers discovered that microwave energy was critical. By bombarding methane and hydrogen molecules with high-frequency microwaves, they could break them apart more efficiently, releasing carbon atoms in a controlled stream. These carbon atoms, once freed, sought the most stable configuration available, the diamond lattice. Under carefully tuned conditions of temperature and gas composition, they deposited smoothly on the seed crystal, building up layer after layer without forming graphite or other contaminants. But to create a super diamond, scientists needed to increase the growth rate dramatically without sacrificing quality. This meant experimenting with gas mixtures, chamber geometries, and electromagnetic fields to accelerate deposition. In some labs, growth rates increased from micrometers per hour to millimeters per day, a 1,000-fold improvement over early methods. Tougher than nature, multi-crystal structures, while single-crystal diamonds are beautiful and extremely hard, they possess a fatal weakness: cleavage planes. These are specific directions in the lattice where the atomic bonds are slightly weaker. Gem cutters exploit them to split diamonds cleanly. In high-stress environments, these same planes can cause catastrophic fractures. The solution came from an unexpected source: carbonado, the black diamonds from space. Their structure is not a single crystal, but a network of millions of microcrystals fused together. This mosaic eliminates the neat cleavage planes of single stones, making carbonado extraordinarily tough and almost impossible to cut. Inspired by this structure, scientists began to grow polycrystalline diamond sheets using CVD, encouraging multiple crystals to nucleate and merge. By controlling the size and orientation of these grains, they could tailor the toughness and other properties of the resulting material. The result was a super diamond composite, harder than any natural diamond, yet far less prone to fracture. For high-performance electronics and extreme engineering applications, this was a game-changer. From seeds to sheets, engineering precision, the versatility of CVD allowed researchers to grow diamonds in forms that were once unimaginable. Instead of waiting for rough stones to be extracted and cut, they could design the shape first, then grow the diamond to match. Need a wafer for a semiconductor? Start with a silicon substrate dusted with diamond seeds. Grow a perfectly flat layer, then polish it to nanometer precision. Need a diamond window for a spacecraft sensor? Create a mold of the desired shape, grow the diamond onto it, and remove the substrate afterward. Need a high-power heatsink? Grow a thick polycrystalline diamond block with boron doping for conductivity. Then integrate it directly with electronic components. This bottom-up engineering fundamentally changed how diamonds were used. Instead of cutting and polishing, the growth process itself became the act of manufacturing. Pushing the limits, Hemley's breakthrough, one of the most striking demonstrations of superdiamond technology, came from the Carnegie Institution for Science in Washington, D.C. Russ Hemley and his team were engaged in high-pressure research, using diamond Anvil cells to recreate the extreme conditions found deep inside planets. These devices squeeze a tiny sample between the tips of two diamonds, generating pressures millions of times higher than at Earth's surface. But there was a problem. Even natural diamonds shattered under the stresses required for next-generation experiments. Hemley's team turned to CVD-grown super diamonds. By growing large, flawless crystals, and then subjecting them to additional high-temperature, high-pressure treatments, they created anvils 50% stronger than the Hope diamond itself. In just 6 days, they grew a 15-carat super diamond, 1/3 the size of the Hope, that broke the lab's hardness gauge. Using these anvils, the team reached pressures previously unattainable, simulating conditions in the Earth's lower mantle and even testing how microbial life responds to crushing forces. The implications stretched far beyond geology. If these super diamonds could withstand such unimaginable stresses, they could serve as the foundation for entirely new classes of machines, sensors, and reactors. Engineering the electronic future. While high-pressure research demonstrated super diamond strength, the electronics industry saw something else: potential disruption. For decades, silicon had been the backbone of computing and communication. But silicon was reaching its physical limits. Diamond, with its exceptional thermal conductivity and ability to be doped with boron for semiconductivity, offered a way out. Diamond-based chips could run at 3 times the speed of silicon while carrying 30 times more power. They could operate at temperatures exceeding 1,800 degrees Fahrenheit without degradation. Imagine cell phones that never overheat, spacecraft electronics that function near the sun, or supercomputers cooled naturally by their own diamond structure. The bottleneck was no longer the material's properties, it was manufacturing at scale. And with advances in wafer-sized polycrystalline CVD, that bottleneck was starting to crack. From myth to machine for centuries, diamonds have inspired myth, from sacred curses to symbols of eternal love. But in clean rooms and research facilities, they were being reborn as something entirely different: machines. The same sparkle that once adorned royal crowns now revealed secrets of thermal transport, electron mobility, and molecular bonding. The same lattice that trapped light so beautifully was now carrying electrical currents and dissipating heat with unparalleled efficiency. This was not simply about making prettier stones. It was about engineering the impossible, taking a material born in dying stars and reimagining it as the backbone of human technology. Part 4: Cosmic Origins. The stellar story of carbon. Long before the first diamond anvil cell was tightened in a laboratory, before methane gas was cracked by microwaves in a CVD chamber, before the Earth itself had cooled, the story of diamonds began in the stars. To understand why this material is so unique, scientists had to trace its origin not to Earth's crust or mantle, but to the furnaces of ancient suns. A universe without carbon. At the birth of the universe, roughly 13.8 billion years ago, there were no diamonds and no carbon. The Big Bang produced mostly hydrogen and helium, with trace amounts of lithium. Elements heavier than these simply didn't exist yet. The early universe was chemically simple, a vast expanse of light gases swirling and clumping under gravity's pull. For carbon to appear, something extraordinary had to happen. Stars had to die. Inside stars like our sun, nuclear fusion turns hydrogen into helium, releasing enormous energy. But fusion can only proceed up the periodic table when the star reaches old age. As a star runs out of hydrogen, it swells into a red giant, its core contracting and heating until new fusion pathways open. Helium begins to fuse, producing carbon through a delicate process known as the triple alpha reaction: 3 helium nuclei colliding to form a single carbon atom. This reaction doesn't happen easily. It depends on finely tuned resonance conditions that allow the carbon nucleus to form briefly and stabilize. Physicists often point to this as one of the most remarkable coincidences in nature. If the resonance energy were slightly different, carbon might not exist at all, and neither would we. The death throes of a star as red giants approach the end of their lives. Their cores become dense carbon and oxygen furnaces. Eventually, the star can no longer sustain the outward pressure needed to balance its gravity. The core collapses, triggering a titanic explosion, a supernova. This is where cosmic alchemy reaches its peak. In that instant, temperatures soar into the billions of degrees, and pressures crush atoms together into heavier elements. The carbon created during the star's lifetime is hurled outward into space in an immense shockwave, spreading the building blocks of future worlds. Astrophysicist Neil deGrasse Tyson once described supernovae as the universe's carbon factories. Without these explosions, carbon would remain locked inside dead stars. Instead, supernovae scatter it across galaxies, seeding interstellar clouds with the dust that will eventually form planets, and, deep within those planets, diamonds. From starlight to bedrock over millions of years, the debris from a supernova slows, cools, and begins to clump under gravity. Some regions become stellar nurseries, collapsing into new stars surrounded by disks of gas and dust. It was in one of these disks that our solar system was born. The early solar system was chaotic. Asteroids collided, protoplanets formed and shattered, and dust from older stars mixed with fresh material. Among this cosmic dust was carbon, the raw material for both life and diamonds. As Earth formed roughly 4.5 billion years ago, enormous quantities of carbon became trapped in its mantle. Here, under crushing pressure and searing heat, some of this carbon began its transformation. Atom by atom, over unimaginable spans of time, carbon rearranged into the dense tetrahedral lattice that defines diamond. But not all diamonds followed this path. Some arrived fully formed, delivered by meteorites that carried carbonado, black diamonds forged not inside Earth, but in the vacuum of space. The mystery of carbonado diamonds have puzzled geologists for over a century. Found in scattered deposits across South America and Central Africa, these black, porous stones do not resemble typical Earth-formed diamonds. When scientists studied them under microscopes, they found something extraordinary: voids. Tiny empty spaces permeate their structure, something that could not survive the immense pressures of Earth's mantle. Even more striking, carbonado is not a single crystal. It is a mosaic of millions of microcrystals, welded together in a way that makes it larger, tougher, and more irregular than any natural gemstone. The prevailing theory is that carbonado was born in space, during the violent collisions of carbon dust particles in the aftermath of a supernova. In the near-perfect vacuum, tiny diamonds bashed into each other, fused through heat, and gradually formed larger, spongy masses. Eventually, meteorites carrying these diamonds slammed into Earth, scattering carbonado across 2 continents. This explains their unusual distribution, not in kimberlite pipes like most diamonds, but in sedimentary deposits far from known volcanic sources. Stellar clues, earthly applications for scientists working to engineer superdiamonds. Carbonado offered more than a cosmic curiosity. Provided a blueprint. If diamonds could form at low pressure in space, then perhaps high-pressure presses weren't the only path to synthesis. Perhaps, under the right conditions of energy and vacuum, carbon atoms could be tricked into assembling into diamond without Earth-like pressures. This insight was critical in the development of low-pressure CVD methods, which now dominate synthetic diamond production. In a way, modern diamond laboratories are miniature stars, replicating the conditions of stellar debris clouds rather than Earth's mantle. By manipulating energy and gas composition, scientists can grow diamonds in forms nature never conceived. A cosmic perspective understanding the stellar origins of carbon does more than explain how diamonds form. It reframes their significance entirely. When we hold a diamond, whether natural or synthetic, we are holding a piece of a dead star. The atoms in its structure were forged in the final moments of a sun-like star's life, scattered across the galaxy, and eventually gathered here. And now, in laboratories across the planet, humans are learning to do what stars once did: assemble carbon into one of the most extraordinary materials in the universe. This cosmic context also hints at possibilities beyond Earth. If carbonado formed naturally in the vacuum of space, could similar processes be happening right now around distant stars? Could exoplanets be rich in diamond crusts or diamond-based geology? Some models suggest that carbon-rich worlds, orbiting stars with different elemental abundances, could be almost entirely diamond planets, spheres of crystalline carbon orbiting alien suns. From the heavens to human hands, in a very real sense, the story of the superdiamond is the story of humanity's relationship with the cosmos. For billions of years, stars forged carbon and scattered it through space. Planets gathered it. Earth shaped some of it into gems. And now, humans, intelligent products of that same stardust, are learning to forge their own diamonds, to bend atomic lattices to their will, to grow sheets and wafers that could power the next era of civilization. The chain has come full circle. From star to stone, from stone to science, from science back to star-like creation. Part 5. The Science of Perfection. Properties that redefine technology. Diamonds have long dazzled human eyes, but their true power lies not in how they look, but in what they are. On the atomic level, a diamond is a masterpiece of natural engineering. Each carbon atom bonded to 4 neighbors in a perfectly rigid tetrahedral structure, forming an infinite three-dimensional lattice. This arrangement gives rise to a constellation of properties that make diamond unlike any other material known to science. When researchers began studying these properties not as curiosities, but as technological tools, they realized they weren't just working with a gemstone. They were dealing with a new class of material, one that could push the boundaries of electronics, mechanics, optics, and even planetary science. Hardness beyond comparison. Diamond's reputation as the hardest natural substance on Earth is well-deserved. On the Mohs scale, it sits alone at the top with a perfect 10, its hardness roughly 4 times that of corundum, the mineral that forms sapphires and rubies. In practical terms, this means diamond can scratch and cut through any other natural material. This extreme hardness arises from the strength of the carbon-carbon bonds and the way they interlock in all directions. In graphite, for example, carbon atoms are arranged in flat sheets that slide easily over one another. In diamond, every atom is tightly locked, leaving no planes of weakness. However, diamond's hardness comes with a caveat. It's also brittle along specific cleavage planes, directions where the atomic bonding is slightly less dense. This is why gem cutters can split diamonds cleanly with a well-placed strike. For industrial applications, this brittleness is a weakness. But scientists have learned to overcome it by growing polycrystalline diamonds, inspired by carbonatose structure. These multicrystal superdiamonds lack clean cleavage planes, making them tougher than any single natural stone. Thermal conductivity. Nature's perfect heat highway, perhaps even more remarkable than its hardness, is diamond's thermal conductivity, the best of any known material. Heat flows through diamond up to 5 times faster than through copper, the metal traditionally used to dissipate heat in electronics. This property comes from diamond's tightly bonded lattice, which allows vibrational energy, phonons, to travel with minimal scattering. In metals, heat is carried mainly by electrons, which can be slowed by impurities and boundaries. In diamond, heat is carried structurally with astonishing efficiency. For electronics, this is revolutionary. As chips become smaller and more powerful, they generate more heat in less space. Managing that heat is one of the biggest challenges in computing and telecommunications. Diamond-based materials offer a natural solution, acting as built-in heat sinks that could allow circuits to run cooler, faster, and longer without bulky cooling systems. Electrical behavior. The boron key on its own, pure diamond is an electrical insulator. Its electrons are tightly bound, leaving no free carriers to conduct current. But this changes dramatically when trace amounts of boron are introduced. Boron atoms, when incorporated into the lattice, contribute free charge carriers, turning the diamond into a p-type semiconductor. This is what gives rare blue diamonds, like the Hope, their distinctive electrical properties. In laboratory-grown diamonds, boron doping can be precisely controlled, allowing scientists to tune the electrical conductivity of the material for different applications. Unlike silicon, diamond maintains its semiconducting behavior even at extreme temperatures. While silicon chips begin to fail above roughly 300 degrees Fahrenheit, diamond-based semiconductors can function above 1,800 degrees Fahrenheit. This means electronics built from diamond could operate in environments that destroy conventional circuits. Inside jet engines, on the surface of Venus, near the sun, or in deep space probes where cooling is limited. Optical clarity across the spectrum. Diamonds are famous for their sparkle, but their optical properties extend far beyond the visible spectrum. Diamond is transparent from ultraviolet to infrared, a range broader than any other known solid. Light passes through with minimal distortion or absorption, making diamond an ideal material for high-power laser windows, spacecraft optics, and advanced sensors. Additionally, diamond slows down light dramatically. When a light beam enters the dense lattice, its speed drops to less than half its normal value in air. This delay, combined with total internal reflection, is what gives cut diamonds their characteristic brilliance. But in engineering terms, this optical density can be harnessed for waveguides, quantum communication systems, and optical computing components. Mechanical stability under extreme conditions beyond hardness. Diamond exhibits extraordinary mechanical stability. It resists corrosion, retains its shape under intense pressure, and remains stable at temperatures that cause other materials to deform or vaporize. This is why diamond tips are used in high-pressure physics experiments. In diamond anvil cells, two small diamonds press against each other with immense force, generating pressures millions of times that of Earth's atmosphere. In these conditions, scientists have observed new phases of matter, replicated planetary cores, and studied how microbes respond to crushing forces. With superdiamonds grown larger and tougher than natural stones, these experiments have pushed even further, reaching pressures once thought unattainable in terrestrial labs. A versatile foundation for future technologies. When these properties are combined, diamond emerges as a truly multifunctional platform. A single piece of engineered diamond can act simultaneously as a heat sink, a semiconductor, an optical window, a structural component capable of withstanding extreme environments. This integration is unprecedented. Silicon, for example, excels as a semiconductor but is fragile and thermally limited. Metals conduct heat well but cannot function as semiconductors. Ceramics are stable but poor conductors. Diamond merges all these strengths into one material. Superdiamonds. Tuning the blueprint. What sets superdiamonds apart from natural stones is control. In the lab, scientists are no longer at the mercy of geological chance. They can tune the size, purity, crystal structure, and dopant levels with extraordinary precision. Need a wafer with high thermal conductivity but no electrical activity? Grow a pure, undoped polycrystalline layer. Need a semiconductor for high-temperature electronics? Introduce controlled boron levels into a single crystal film. Need a robust optical window for a deep space probe? Grow a large, flawless sheet and polish it to nanometer smoothness. The combination of these capabilities is why researchers say diamonds are poised to replace silicon in many applications, not just as a better semiconductor, but as a holistic material that can unify multiple functions in a single component. Why this matters now. For decades, diamonds' extraordinary properties were curiosities, studied in academic papers and displayed in museum cases. But as manufacturing technologies caught up, these properties became practical tools. With advances in CVD and polycrystalline growth, industries can now access large, engineered diamond sheets and shapes that were unimaginable just a generation ago. The shift is similar to what happened with silicon in the mid-20th century. Once, silicon was just sand. Then, through refinement and engineering, it became the backbone of modern civilization. Today, diamonds are undergoing that same transformation, from rare gems to industrial foundations for a new technological era. Here is Part 6, Beyond Silicon. A new technological frontier. For more than half a century, silicon has been the quiet engine of modern civilization. It powers our computers, smartphones, satellites, and entire communication networks. It enabled the microchip revolution, shrinking room-sized machines into pocket devices. But every technology has limits, and silicons are fast approaching. The challenge is simple but fundamental. As circuits become smaller and denser, the amount of heat they produce skyrockets. Silicon, though an excellent semiconductor, begins to falter when its temperature climbs above about 300 degrees Fahrenheit. Once that threshold is crossed, performance degrades, leakage currents increase, and chips can fail catastrophically. Engineers compensate by building complex cooling systems, fans, heat sinks, even liquid cooling to keep silicon operational. But this adds weight, cost, and inefficiency. The modern semiconductor industry has been remarkably resourceful in stretching silicon's capabilities, but the physics is unforgiving. Miniaturization is reaching atomic scales, and thermal bottlenecks threaten to stall the progress of Moore's law. The search for a next-generation semiconductor isn't just about speed, it's about survival. Diamonds enter the stage in this context. Diamond has emerged as the most promising successor. Its combination of unparalleled thermal conductivity, high breakdown voltage, and semiconducting capability, when doped, makes it a candidate to supersede silicon in the most demanding applications. While silicon chips can handle power densities measured in tens of watts per square centimeter, diamond-based devices could theoretically handle hundreds, even thousands, without overheating. Their ability to operate at high temperatures means they could function in environments that would instantly destroy silicon electronics. Deep inside engines, on planetary surfaces like Venus, or in the intense radiation belts around giant planets. Power electronics revolution. One of the most immediate applications of diamond semiconductors is power electronics, the systems that manage and convert electrical energy in everything from power grids to electric vehicles. Modern power devices rely heavily on silicon carbide, SiC, and gallium nitride, GaN, both of which outperform pure silicon in terms of heat resistance and voltage handling. Yet, even these advanced materials pale compared to diamond. Diamond has a bandgap of 5.5 electron volts, the highest of any known semiconductor. This means it can sustain huge voltages without breaking down, making it ideal for power transmission and conversion. It can also carry 30 times more current than silicon while operating at 3 times the speed. Imagine electric grids that lose less energy to heat. Electric vehicles with lighter, more efficient power systems. High-speed trains, industrial machines, and renewable energy infrastructure running on diamond-based electronics that hardly need cooling. The potential efficiency gains are staggering. High-frequency communication. Another frontier is radio frequency, RF, and microwave electronics. These are the technologies that drive cell towers, radar systems, satellite links, and advanced military communications. Diamond's ability to conduct heat means RF amplifiers built on diamond could run at higher power levels and higher frequencies without overheating. Today's silicon and gallium-based RF devices face thermal bottlenecks that limit their output and require bulky, expensive cooling systems. Diamond could remove those bottlenecks entirely, enabling smaller, more efficient, and longer-lasting communication infrastructure. Space exploration and extreme environments. Perhaps nowhere are diamond's advantages more striking than in space exploration. Spacecraft electronics must endure radiation, temperature extremes, and vacuum conditions that push silicon to its breaking point. Cooling is difficult in space. There's no air to carry heat away. Traditional electronics must be heavily shielded and temperature-controlled, consuming power and mass. Diamond devices, by contrast, can operate naturally in extreme environments. They can tolerate temperatures above 1,800 degrees Fahrenheit, resist radiation damage, and dissipate heat through their own structure. This makes them ideal for deep space probes, landers on hot planets, or satellites operating close to the sun. Future spacecraft could carry diamond-based sensors, communication systems, and processors that need little or no cooling, freeing engineers to design lighter and more capable missions. Defense and strategic systems beyond civilian uses. Diamond electronics have attracted interest from defense sectors. In combat zones, equipment must endure dust, heat, shock, and electromagnetic interference, conditions that often cause silicon-based systems to fail. Diamond's resilience makes it ideal for battlefield communications, radar, energy weapons, and high-power signal processing. Nanoscale diamond resonators, for example, can vibrate up to 100 billion times per second, creating the clearest radio signals ever achieved. These resonators are thousands of times smaller than a human hair, yet tough enough to survive intense mechanical and thermal stress. Manufacturing challenges. For all these advantages, diamond electronics still face serious manufacturing hurdles. Growing large, defect-free diamond wafers suitable for semiconductor fabrication is technically demanding. CVD methods have improved dramatically, but achieving uniform doping and surface smoothness at wafer scale remains expensive and time-consuming. Silicon benefits from a mature, global infrastructure, refineries, fabs, supply chains built over decades. Diamond technology is comparatively young. Scaling up production to meet the needs of massive industries like computing and telecommunications will require new fabrication methods, investment, and time. However, these challenges are engineering problems, not physical ones. The fundamental physics of diamond is already superior to silicon. And as costs fall and processes improve, its adoption is expected to accelerate, particularly in niche, high-value sectors first, like aerospace, defense, and advanced power electronics, before eventually spreading to consumer technologies. Rethinking device architecture. Another exciting possibility is that diamond could reshape how electronics are designed, not just what they're made of. Because diamond can act as both a heat sink and a semiconductor, entire device architectures could be simplified. Components that today require multiple materials, silicon chips bonded to copper heat spreaders and enclosed in ceramic packages, could be integrated into a single diamond substrate, reducing complexity and improving performance. Diamond's wide optical transparency could also enable integrated optoelectronic systems, where photonic and electronic components are built on the same platform. This is a vision beyond simply replacing silicon. It's about redefining electronics from the ground up. The coming transition, the semiconductor industry rarely changes its foundational material. The last great shift was from germanium to silicon in the mid-20th century, a change that enabled the modern digital era. If diamond replaces silicon, even partially, it will be one of the most profound technological transitions in modern history. This transition will likely follow a familiar pattern, first in specialized high-performance sectors, where diamond's advantages justify its higher cost, then gradually expanding as manufacturing scales and costs drop. In the decades to come, we may look back on silicon the way we now look at vacuum tubes, a revolutionary material that laid the groundwork, but ultimately gave way to something better. Part 7. Engineering Breakthroughs. Growing the perfect crystal to turn diamond into a reliable, scalable foundation for future technologies. Scientists had to solve a series of extraordinarily difficult engineering problems. Natural diamonds are remarkable, but they are geological accidents. Flawed, irregular, and inconsistent. To replace silicon, engineers needed something very different. Large, flawless, uniform diamond wafers, grown on demand, shaped to precise specifications, and controllable at the atomic level. This was not just a matter of making diamonds bigger. It was about learning to control nature's most rigid structure as if it were clay. The challenge of size and purity in nature. Most diamonds are small, measured in millimeters. Gem-quality stones larger than a few carats are rare, and defect-free crystals even rarer. Industrial synthetic diamonds made by high-pressure presses are typically smaller still. But semiconductor wafers need to be large, typically several inches across, and nearly perfect with minimal dislocations or inclusions. Early attempts to grow larger diamonds using traditional high-pressure methods ran into fundamental barriers. The pressure vessels could only accommodate small reaction volumes, and as the crystal grew, internal stresses caused it to fracture. Moreover, impurities from the metal catalysts used in growth often contaminated the lattice, ruining its electronic properties. The breakthrough came when researchers realized that size and purity were linked to control, not brute force. If they could manage the environment in which carbon atoms assembled, they could guide the growth, ensuring the lattice formed uniformly without unwanted phases like graphite. CVD, from concept to precision tool chemical vapor deposition (CVD), had existed since the mid-20th century, but for decades it was a laboratory curiosity, slow, finicky, and prone to producing flawed films. In the 1990s and early 2000s, advances in microwave plasma technology, vacuum control, and computational modeling transformed CVD from a concept into a precision growth tool. In a typical microwave plasma CVD system, a small seed crystal is placed in a vacuum chamber heated to roughly 3,600 degrees Fahrenheit. A mixture of methane and hydrogen gas is introduced. Microwave energy excites the gases, forming a glowing plasma in which carbon atoms are stripped from methane. The hydrogen atoms etch away any graphite that forms, ensuring that only diamond grows. Carbon atoms in the plasma gradually settle onto the seed, locking into the tetrahedral lattice. By carefully controlling gas composition, pressure, temperature, and microwave power, scientists can manipulate the growth rate and the resulting crystal quality. What was once measured in micrometers per hour can now reach millimeters per day, thanks to decades of refinement. For the first time, it became feasible to grow large single-crystal diamonds, not just for jewelry but for electronics. Overcoming defects. One of the key challenges in diamond growth is avoiding defects, microscopic disruptions in the crystal lattice that can dramatically affect performance. Dislocations, grain boundaries, and inclusions can scatter electrons, weaken mechanical strength, and interfere with optical transparency. Scientists developed sophisticated techniques to monitor and control defect formation during growth. They use in situ spectroscopy to watch the plasma, X-ray topography to detect dislocations, and computational models to predict how stresses evolve inside growing crystals. One major improvement was substrate preparation. By polishing and orienting seed crystals along specific crystallographic planes, researchers minimized unwanted nucleation sites. This allowed the diamond to grow layer by layer, like bricks stacking perfectly in a wall, rather than chaotically like a pile of gravel. Wafer-scale growth. Perhaps the most significant milestone was achieving wafer-scale growth, producing diamond films several inches across with uniform thickness and properties. This is crucial for semiconductor manufacturing, which depends on standardized wafer sizes to fit existing fabrication lines. To do this, researchers seed silicon wafers with tiny diamond particles, creating a dense array of nucleation sites. When the wafer is placed into the CVD chamber, each seed grows outward until the individual crystals merge into a continuous film. The result is a polycrystalline diamond wafer, with grain sizes and orientations carefully controlled to optimize performance. These wafers can then be lifted off their silicon substrates, polished, doped, and processed using techniques adapted from the semiconductor industry. The result? Thin, robust diamond sheets, ready for integration into high-performance electronics. Boron doping and electronic control. Controlling the electrical properties of diamond is just as important as controlling its size and purity. In its natural state, diamond is an insulator. But with the addition of boron atoms during CVD growth, scientists can turn it into a semiconductor. Boron atoms substitute for carbon in the lattice, introducing holes, positive charge carriers, that allow current to flow. By adjusting the boron concentration, engineers can fine-tune the conductivity, from barely conductive to strongly p-type. More recently, researchers have explored n-type doping using elements like phosphorus, although this remains more difficult. Achieving reliable n-type diamond could open the door to full transistor circuits built entirely from diamond, paving the way for ultra-fast, ultra-durable computing devices. Advanced growth geometries. CVD growth isn't limited to flat wafers. Because the process builds diamond atom by atom, it can be adapted to grow complex shapes. Engineers can deposit diamond onto molds, curved substrates, or even pre-existing components, coating them with a diamond layer that conforms exactly to their shape. This has led to innovations like diamond-coated turbine blades, high-precision cutting tools, and optical components with diamond layers for durability and thermal stability. For electronics, it means that heat spreaders and structural components can be grown directly as part of the device, rather than attached later. The push for perfection. Even with all these advances, the quest for the perfect diamond continues. Defect densities in lab-grown crystals are still higher than in the rarest natural stones, and scaling to larger wafers without introducing stress remains a challenge. However, progress is rapid. Each year, growth rates improve, wafers get larger, and defect levels drop. Research labs and private companies are investing heavily, aiming to make diamond wafer production as routine as silicon within the coming decades. A new kind of material science. What makes this engineering revolution unique is that it blurs the line between natural formation and human design. For billions of years, diamonds formed deep underground or in the vacuum of space, their structures dictated by the impersonal forces of physics. Now, in climate-controlled labs, humans are directing those same forces, shaping carbon atom by atom into crystals that exceed anything nature has made. This is not just replication. It is mastery, an unprecedented level of control over one of the universe's toughest and most fascinating materials. Here is Part 8, Cracking the Code. Overcoming the final barriers. By the early 21st century, diamond growth technology had moved from speculative science to a powerful industrial tool. Microwave plasma reactors could grow flawless sheets of crystal. Wafer-scale polycrystalline diamonds were being produced with increasing consistency. Boron doping had turned these crystals into tunable semiconductors. And yet, despite these remarkable achievements, a set of formidable barriers remained between diamond and its full technological promise. These were not barriers of imagination or physics. They were barriers of engineering, economics, and scale, the kinds of challenges that determine whether a breakthrough remains a laboratory triumph or becomes a civilization-shifting technology. Barrier 1. Scaling up without sacrifice. Silicon's dominance isn't just about its properties. It's about infrastructure. Over decades, the semiconductor industry built an entire global ecosystem around silicon. Ultrapure crystal pulling methods, massive wafer fabs, automated photolithography, and economies of scale that drove costs down dramatically. For diamond to compete, it must not only match silicon's performance but scale up its production to similar levels of reliability and uniformity. Growing a few flawless wafers in a lab is one thing. Producing thousands of identical wafers week after week is another entirely. Diamond's growth environment is more complex than silicon's. Microwave plasma reactors require extremely stable temperature and pressure conditions, and even slight variations can introduce defects or stress. Uniform doping across large wafers remains challenging. Unlike silicon, which can be grown as huge single crystals and sliced into wafers, diamond growth is inherently a bottom-up process that must be carefully managed layer by layer. Researchers have made impressive progress, but achieving industrial-scale reproducibility remains one of the biggest hurdles. Barrier 2. Cost and economics. Silicon's cost advantages are staggering. Raw silicon is derived from sand, one of the most abundant materials on Earth. Ultrapure silicon wafers cost only a few dollars each, thanks to decades of refinement. Diamond, by contrast, requires energy-intensive growth inside specialized vacuum chambers. Boron doping involves expensive precursors, and growth times, though improving, are still measured in days, not hours. For specialized aerospace or defense applications, these costs are manageable. But for mass-market electronics, smartphones, laptops, cloud servers, every penny counts. Until diamond wafers can be produced cheaply and quickly, their adoption will remain limited to high-value niches. However, history offers a precedent. Early silicon transistors were far more expensive than vacuum tubes, but as production scaled, costs plummeted. Many in the field believe diamond is following the same trajectory, it's just at an earlier stage. Barrier 3. N-type doping. While boron doping allows diamond to act as a p-type semiconductor, achieving reliable N-type doping has proved extraordinarily difficult. Phosphorus has been used experimentally, but its incorporation into the diamond lattice is inefficient, and the resulting carrier mobilities are low. Without robust N-type doping, it's difficult to build complementary logic circuits, the kind that form the backbone of modern computing. This limits diamond's immediate applications in complex microprocessors, though it remains ideal for high-power and high-frequency devices where p-type conduction suffices. Cracking the N-type doping problem is one of the key scientific frontiers in diamond electronics today. Several research groups are exploring alternative dopants, novel implantation methods, or hybrid diamond semiconductor structures to overcome this challenge. Barrier 4. Integration with existing technology. Even if diamond wafers were cheap and plentiful tomorrow, integrating them into existing semiconductor fabrication lines would not be trivial. Silicon fabs are designed around specific wafer sizes, etching chemistries, and lithography techniques. Diamond behaves differently. It's chemically inert, extremely hard, and thermally conductive in ways that challenge conventional processing equipment. Etching diamond requires plasma-based methods with specialized gases, and bonding diamond to other materials demands careful management of thermal expansion mismatches. Hybrid approaches are emerging. Some companies are exploring diamond-on-silicon wafers, where thin diamond layers are grown on silicon substrates, combining diamond's thermal advantages with silicon's mature processing ecosystem. Others are experimenting with diamond interposers that act as heat spreaders and electrical layers beneath conventional chips. These transitional solutions may bridge the gap between existing silicon infrastructure and future diamond-dominant systems. Barrier 5. Knowledge and workforce. Another less visible but critical barrier is expertise. Silicon has benefited from decades of academic programs, industry training, and standardized methods. Diamond growth and processing are comparatively new, and the number of specialists worldwide remains limited. To push diamond technology forward, universities, industries, and governments will need to invest in training a new generation of materials scientists, electrical engineers, and fabrication experts fluent in diamond's unique behavior. This is beginning to happen, but it will take time to match silicon's vast knowledge base. Early solutions and emerging strategies. Despite these barriers, momentum is building. Several strategies are converging to bring diamond electronics closer to commercial reality. Hybrid wafers. Diamond layers bonded to silicon wafers, allowing gradual integration into existing fabs. Dedicated diamond fabs. Companies are investing in specialized facilities designed specifically for CVD growth and diamond device fabrication. Cost reduction. Advances in reactor design are cutting growth times and increasing yields, while competition among manufacturers is driving prices down. Focused applications. Industries like aerospace, defense, and power electronics are adopting diamond first, where performance matters more than cost, driving demand and experience. These approaches mirror the early days of silicon, when the technology was initially expensive and niche before economies of scale transformed it into a universal material. A different kind of technological revolution. It's important to recognize that diamond may not replace silicon overnight. The transition will likely be gradual, with hybrid systems dominating for years or decades. In many cases, diamond will complement silicon, handling thermal management, high-power switching, or extreme environment operation, while silicon continues to serve mainstream computing needs. Over time, as costs fall and manufacturing matures, fully diamond-based systems may emerge, reshaping industries from computing to energy to space exploration. The lessons of history. Every major technological material, from bronze to steel, from vacuum tubes to transistors, has faced a critical moment when scientific promise collided with practical obstacles. Those that succeeded did so not by overcoming physics, but by overcoming engineering. Diamond stands at that same threshold now. The science is sound. The properties are unmatched. What remains is to crack the code of large-scale production, integration, and cost. A challenge formidable but not insurmountable. Here is Part 9: Expanding Horizons. Global impacts and new possibilities. As the engineering barriers surrounding super diamonds begin to crumble, the world is starting to imagine what their widespread adoption could mean. Beyond laboratories and specialized aerospace missions, diamond-based technologies carry the potential to reshape entire industries, restructure global supply chains, and even alter geopolitical balances. The rise of super diamonds is not just a scientific story. It's an economic, environmental, and strategic one. Global industry transformation. If diamond-based semiconductors become commercially viable at scale, their impact on the global electronics industry would be profound. Silicon dominates because of its mature ecosystem, but its physical limitations are increasingly visible in data centers, power infrastructure, and high-performance computing. Replacing even a fraction of this ecosystem with diamond wafers would trigger a technological and economic transformation on a scale similar to the semiconductor boom of the mid-20th century. Entire fabrication plants would need to be redesigned. Supply chains for raw materials would shift away from sand refining towards CVD gas mixtures, plasma reactor components, and specialized diamond processing tools. Countries that currently lead in silicon production, like the United States, Taiwan, South Korea, Japan, and China, would compete to secure leadership in diamond electronics, triggering a new wave of technological competition. Energy and climate impact. One of the most promising impacts of super diamond technology lies in energy efficiency. Modern data centers consume staggering amounts of electricity, much of it spent on cooling silicon chips. These facilities are responsible for a growing share of global carbon emissions. Diamond-based chips, with their exceptional thermal conductivity, could operate at much higher power levels without extensive cooling systems. This could reduce energy consumption dramatically, cutting costs and emissions simultaneously. Power electronics based on diamond could also improve the efficiency of electrical grids, reducing losses during transmission and conversion. In electric vehicles, diamond power modules could lead to lighter, more efficient systems, extending range and reducing charging times. In an era where energy efficiency is not just a technological goal but a global necessity, diamond's properties align perfectly with environmental priorities. Aerospace and space exploration. The aerospace sector stands to be one of the earliest large-scale beneficiaries of super diamond technology. Aircraft, rockets, and satellites operate in extreme conditions: high radiation, vacuum, intense heat, and severe mechanical stress. Silicon electronics must be heavily shielded and cooled, adding weight and complexity to every mission. Diamond electronics can thrive in these conditions naturally. Components made from diamond could operate close to rocket engines, withstand cosmic radiation during long-duration missions, and function reliably in the temperature swings of deep space. Imagine a spacecraft powered by diamond-based circuits, its sensors and processors functioning seamlessly on the blistering surface of Venus or within the intense magnetic fields of Jupiter. Diamond's resilience could extend mission lifetimes, reduce shielding requirements, and enable entirely new classes of exploratory probes that go where silicon cannot survive. Defense and strategic advantages. Diamond's unique properties also carry strategic implications. Nations that master diamond semiconductor technology first will hold significant advantages in military communications, radar, energy weapons, and secure computing. Diamond nanoresonators, for example, can generate extremely precise radio signals at frequencies much higher than conventional oscillators. In military networks, this translates into faster, clearer, more jam-resistant communications. High-power radar systems built on diamond could detect objects at greater ranges while remaining compact and thermally stable. Directed energy weapons could use diamond-based power modules to sustain higher outputs with less cooling, making them more practical for deployment. As with any transformative material, technological leadership may translate directly into geopolitical power. Economic realignment. Super diamonds also promise to disrupt existing resource economies. The current diamond industry is structured around mining and gemstone markets, with a complex web of trade routes, cartels, and luxury branding. As synthetic diamonds surpass natural ones in performance and scale, the center of economic gravity may shift away from mining regions toward high-tech manufacturing hubs. Countries investing in plasma reactor infrastructure and diamond fabrication facilities could become the new economic powerhouses of this industry, while traditional mining operations may face rapid decline. This shift mirrors what happened to natural rubber industries after the rise of synthetic rubber, or whale oil markets after the advent of petroleum. The value of a diamond will no longer be measured in carats or clarity, but in crystal uniformity, dopant precision, and wafer yield. Ethical and environmental implications. Unlike traditional diamond mining, which often involves significant environmental damage and human rights concerns, lab-grown diamonds can be produced with relatively low ecological impact. CVD processes do require energy, but they avoid the deforestation, habitat destruction, and exploitative labor practices associated with mining. As demand for high-performance diamonds grows, ethical sourcing may shift from mines to reactors, reshaping consumer perceptions and regulatory frameworks. Conflict-free could eventually mean not just avoiding war zones, but using entirely synthetic materials. A catalyst for new technology. Super diamonds are not just replacements for existing materials. They may enable entirely new kinds of technologies. For example, quantum devices. Diamond's nitrogen vacancy centers can act as stable quantum bits, enabling sensors and quantum computers that operate at room temperature. Integrated photonics. Diamond's optical transparency and high refractive index make it an ideal platform for combining photonic and electronic circuits. Ultra-durable medical implants. Diamond's biocompatibility and stability could lead to implants that last for decades without degradation. Extreme environment robotics. Diamond electronics could enable machines to function in volcanic vents, nuclear reactors, or deep planetary interiors. These applications go beyond simply making faster computers. They open entirely new domains of exploration and capability. Global collaboration and competition. As with past technological revolutions, the rise of diamond electronics will likely feature a mix of international collaboration and intense competition. Universities, private companies, and national research agencies are already forming alliances to advance diamond growth techniques, share reactor designs, and standardize fabrication methods. At the same time, countries recognize the strategic value of diamond technologies. Patent races, export controls, and research secrecy are becoming more common, reminiscent of the early days of nuclear energy or space exploration. A parallel to the Silicon Revolution in many ways, what's happening with diamonds now mirrors the Silicon Revolution of the 1950s and 1960s. Back then, few could have imagined that a humble material derived from sand would spawn the global information age. Today, diamonds, once symbols of luxury and permanence, are being reborn as the backbone of a new technological era. The difference is scale. Silicon changed communication and computation. Diamond may change everything from energy and transportation to planetary exploration. Here is Part 10, a turning point in science and society throughout history. Certain materials have acted as inflection points for civilization. Bronze enabled the first great empires. Iron reshaped warfare and agriculture. Steel built railways and skyscrapers. Silicon unlocked the digital age. Each of these materials did more than improve existing technologies. It redefined what societies could do, altering economies, geopolitics, and even culture. Diamond now stands poised to join this lineage. Not the rare gemstones of legend, but engineered diamond, atomically precise, reproducible, and scalable. Its arrival signals not just the next chapter in materials science, but a potential paradigm shift in how humanity interacts with technology, energy, and the cosmos. From luxury to utility for centuries, diamonds were symbols of wealth, status, and permanence. Their value came from their rarity, not their functionality. That perception is changing rapidly. In laboratories around the world, diamonds are no longer treasured for their sparkle, but for their thermal conductivity, semiconducting potential, and structural strength. This transition from luxury to utility is profound. It mirrors the way aluminum transformed from a precious metal more valuable than gold in the 19th century to the backbone of modern aviation and construction in the 20th. What was once ornamental is becoming fundamental. Scientific tools that transform science itself. Diamond is not just enabling new industries. It's also changing the way science is done. In high-pressure physics, diamond and Ville cells have opened windows into conditions once thought unreachable, allowing researchers to simulate planetary cores, create new materials, and observe exotic phases of matter. With superdiamond anvils, scientists are now pushing pressures beyond those at the center of Earth, venturing into regimes relevant to exoplanets and stellar interiors. In quantum science, defects in diamond lattices, specifically nitrogen vacancy centers, have emerged as some of the most promising candidates for quantum sensors and qubits. These tiny imperfections can detect magnetic and electric fields with unprecedented sensitivity, operate at room temperature, and remain stable for long periods. They are already being used to study biological systems, image brain activity, and test fundamental physical theories. In other words, diamond is not just another tool in the scientific arsenal. It's a platform that enables entirely new kinds of experiments and devices, accelerating discovery across multiple fields. Educational shifts and workforce evolution. As diamond technology matures, education and industry are beginning to adapt. Universities are creating new programs focused on diamond electronics, plasma growth techniques, quantum sensing, and high-power systems. Interdisciplinary collaborations between materials science, electrical engineering, and quantum physics are becoming essential. This echoes the early days of the Silicon Revolution, when new curricula and research centers sprang up to train the engineers who would build the modern computer age. A similar transformation is now underway, preparing a workforce fluent in diamond-based technologies that will shape the mid-21st century. Ethics and accessibility. As with all transformative technologies, the rise of engineered diamonds raises ethical and societal questions. Who will control this technology? Will it exacerbate global inequalities or help level them? On one hand, diamond growth reactors are expensive and complex, potentially concentrating power in technologically advanced nations and corporations. On the other, diamonds' raw inputs, carbon, hydrogen, energy, are abundant, meaning that with the right knowledge and investment, many nations could participate in the new diamond economy. Policymakers are already debating export controls, intellectual property frameworks, and international cooperation to ensure that diamond technology develops in a way that benefits humanity broadly, rather than a select few. Cultural shifts. The cultural symbolism of diamond may also undergo a radical transformation. A material once associated with eternity and romance may soon be associated with energy grids, space probes, quantum computers, and medical implants. This shift from personal ornament to civilizational infrastructure is unprecedented. Imagine future generations associating diamonds not with jewelry, but with the devices that power their world, the way today's society associates silicon not with sand, but with microchips. A bridge to the stars. Perhaps the most poetic aspect of this transformation is its cosmic symmetry. Carbon atoms were forged in the hearts of dying stars, scattered across galaxies, gathered into planets, and now, billions of years later, intelligent beings are reshaping them into technologies that may carry us back into space. Diamond electronics could power deep space probes that endure decades in harsh interstellar environments. Diamond optics could enable next-generation telescopes with unmatched clarity. Diamond quantum sensors could map gravitational fields or detect cosmic phenomena with exquisite precision. In this sense, engineered diamond is not just a technological tool, but a cosmic artifact, a way for the universe to understand itself through the minds and hands of its inhabitants. A defining moment. The convergence of scientific maturity, industrial capability, and global necessity makes the rise of diamond technology feel inevitable. Climate change demands more efficient energy systems. Computing demands materials that can go beyond silicon. Exploration demands resilience in the harshest environments. Diamond, with its unique blend of properties, answers all these calls simultaneously. Few materials in history have aligned so perfectly with the grand challenges of their time. We may look back on this era as the moment when diamond moved from myth to mechanism, from luxury to infrastructure, from star dust to civilization's backbone. Like bronze, iron, steel, and silicon before it, diamond stands at the threshold of a new epoch, one in which its role will be measured not in carats, but in the depth of its impact on science, technology, and human destiny. Part 11. The Road Ahead. A vision of the diamond age. The story of engineered diamonds is still being written. The breakthroughs of recent decades have laid the foundation, but the true diamond age lies ahead, a period in which this extraordinary material could reshape every layer of human civilization, from the devices in our pockets to the spacecraft that venture beyond the solar system. Unlike earlier technological transitions, this one is unfolding in a globally interconnected world, amid unprecedented challenges: climate change, resource scarcity, energy transitions, and the digital revolution. Diamond technology does not emerge in isolation. It arrives at a historical crossroads, offering powerful tools just as humanity faces some of its most complex problems. Short-term horizon, next 5 to 10 years. In the near future, diamond technologies will likely focus on niche, high-value sectors, areas where their unique properties deliver advantages that justify higher costs. Power electronics. Diamond components will begin appearing in specialized converters, grid infrastructure, and electric transportation systems. Their ability to handle high voltages and temperatures with minimal cooling will make them ideal for critical energy applications. Aerospace and defense. Diamond-based RF amplifiers, radar components, and heat-resistant circuits will enable lighter, more robust systems. Satellites and probes will integrate diamond electronics for missions in harsh environments. Quantum sensing. Nitrogen vacancy centers in diamond will power the next generation of magnetometers, navigation systems, and medical imaging devices that operate at room temperature with unprecedented sensitivity. Advanced optics. Diamond windows, mirrors, and coatings will find increasing use in high-power lasers, fusion reactors, and telescopes. During this phase, the key drivers will be performance and reliability, not cost. Diamond will sit alongside silicon and compound semiconductors in hybrid systems, gradually proving its worth in real-world deployments. Medium-term horizon, 10 to 20 years. As production methods mature and costs fall, diamond's reach will expand rapidly. Wafer-scale growth will become more routine, doping methods more versatile, and integration with existing fabrication infrastructure more seamless. Data centers and computing. Diamond-based chips could begin replacing silicon in high-power processors, drastically reducing cooling costs and energy consumption. Quantum processors based on diamond defects could emerge as commercially viable platforms. Transportation, electric vehicles, aircraft, and high-speed rail systems will adopt diamond power modules to improve efficiency, range, and durability. Medical and industrial applications. Diamond's biocompatibility and stability will lead to ultra-durable implants, sensors, and diagnostic devices. In heavy industries, diamond coatings and electronics will extend the lifespan of machinery and enable new types of manufacturing under extreme conditions. Climate infrastructure. Diamond power devices will underpin renewable energy grids, enabling more efficient transmission, storage, and conversion of clean power. This stage will mirror the explosive growth of silicon in the 1960s and 70s, as economies of scale drive prices down and open new markets. Long-term horizon, 20 to 50 years. Looking further ahead, the diamond age could mark a fundamental shift in how technology interacts with the physical and cosmic environment. Fully diamond-based electronics. Entire circuits, processors, memory, sensors may be built from diamond, operating at extreme temperatures and power densities unthinkable with silicon. Diamond planetary probes. Autonomous probes equipped with diamond-based systems could explore gas giant interiors, lava worlds, or the surfaces of Venus without failing. Energy systems. Diamond's thermal and electronic properties could enable fusion reactors, ultra-efficient power grids, and distributed energy systems that reshape how civilization uses power. Quantum networks. Diamond quantum nodes may form the backbone of global quantum communication systems, linking continents through secure, high-speed channels. Architectural and structural integration. Diamond composites may appear in buildings, transportation systems, and even personal devices, combining strength, thermal control, and electronics in ways that blur the line between structure and circuitry. At this horizon, diamond will not just replace existing materials, it will enable technologies that simply aren't possible with anything else. Potential risks and uncertainties. No technological revolution comes without risks. The diamond age will bring its own set of challenges. Resource and energy demands. While diamond growth relies on abundant elements, it requires significant energy input. Sustainable reactor operation will be essential to prevent environmental trade-offs. Geopolitical competition. As nations race to secure leadership, diamond technology could become a new axis of strategic rivalry, similar to oil in the 20th century or microchips today. Technological lock-in, over-reliance on a single material ecosystem can create vulnerabilities. Diversification and redundancy will remain important. Ethical concerns. Control over diamond growth technology, from intellectual property to export restrictions, may shape global equity in profound ways. These uncertainties highlight the importance of deliberate governance, international cooperation, and long-term planning. A convergence of disciplines. What makes the diamond age especially remarkable is the way it unites disparate fields. It brings together astrophysics through the cosmic origins of carbon material science, through atomic scale growth and doping electronics, through semiconductors and power systems quantum science, through defect-based computation and sensing mechanical engineering, through coatings and structural integration environmental science, through energy-efficient infrastructure. This convergence mirrors the multidisciplinary synergy that defined the information age, but on an even broader scale. A new technological identity. Future generations may look back and identify the Diamond Age not by a single invention, but by a shift in mindset. It will be the era when humanity mastered one of the universe's hardest materials, not by extracting it, but by growing it, atom by atom, wafer by wafer, reactor by reactor. Just as the Bronze Age wasn't about bronze trinkets, but about reshaping societies around new capabilities, the Diamond Age will be about reshaping civilization itself around a material that merges strength, precision, and cosmic heritage. The first glimmers of the Diamond Age. Even now, the signs are visible. In research labs, diamond wafers shimmer under plasma light. In aerospace cleanrooms, engineers fit diamond-based circuits into satellite housings. In quantum optics labs, diamond defects hum quietly as they detect fields invisible to any other sensor. These are the early whispers of a transformation that, in time, may echo as loudly as the rise of silicon did half a century ago. Here is Part 12 Conclusion. The Spark of a New Era. Part 12 Conclusion. The Spark of a New Era. The story of Diamond, from the hearts of stars to the hearts of human reactors, is a story about transformation. Not just the transformation of carbon into crystal, but of civilization itself as it learns to shape the fundamental building blocks of the universe with precision and intent. We began with a material known for its beauty, rarity, and symbolism. We end with a material that may define the technological infrastructure of the future, a bridge between cosmic history and human destiny. A material older than Earth, a technology younger than a lifetime. Carbon atoms that make up diamonds were forged billions of years ago in the cores of dying stars. For eons, they drifted through space, were caught in the gravity of a young Earth, and eventually formed crystals deep underground. Humans uncovered these stones, marveled at their brilliance, and assigned them value. Then, in the span of just a few decades, humanity learned to do what nature and stars had done, but on demand, with control, and for purposes far beyond adornment. This rapid leap is one of the most extraordinary achievements in materials science. More than a replacement, diamond is not simply better silicon. It represents a different technological paradigm. Where silicon enabled smaller, faster, cheaper computing, diamond offers something broader. Devices that operate in extreme heat and radiation, power systems that waste less energy, sensors that reach quantum precision, structures that merge electronics, optics, and mechanics seamlessly. This is not an incremental upgrade. It's a qualitative shift, a new way of designing machines, infrastructure, and exploration. A mirror of humanity's trajectory. Every era-defining material reflects something about the society that embraces it. Bronze reflected the rise of complex urban cultures. Steel reflected the ambition to build outward and upward. Silicon reflected the drive to miniaturize and connect. Diamond, with its stellar origin and engineered future, reflects a civilization that has looked to the stars, mastered atomic structures, and is now ready to apply that mastery to reshape its relationship with energy, environment, and exploration. Challenges, but no turning back. Significant obstacles remain. Cost, scalability, N-type doping, integration with existing infrastructure. But these are engineering challenges, not physical impossibilities. History has shown that once a material demonstrates decisive advantages, industry finds a way to make it viable. The momentum is clear. Governments, research institutions, and private companies are investing. Wafer growth techniques are improving year by year. Applications are emerging. The pieces are aligning. The Diamond Age beckons. The term Diamond Age has often been used metaphorically, evoking images of futuristic societies and advanced materials. But here, it's not metaphor. It's a real, unfolding era in which diamond becomes central to the way we generate power, compute information, explore the cosmos, and design the built environment. It's the age when humanity no longer relies solely on the Earth to provide rare materials, but creates them with precision. When the same carbon atoms that once floated through space are transformed into the cores of quantum computers, the heat spreaders of planetary probes, and the circuits of energy grids. It's the age when what was once a symbol of permanence becomes a symbol of progress. A spark, not an endpoint. As with all great transformations, the rise of diamond technology will not happen overnight. It will come in waves, spreading from laboratories to industries, from industries to infrastructure, and from infrastructure to daily life. But the spark has been lit. Plasma reactors hum in research facilities. Quantum sensors made of diamond are mapping invisible forces. Wafer-scale growth lines are being refined. Aerospace engineers are pushing the limits of what these crystals can endure. The trajectory is set outward, upward, and into new realms of possibility. A final reflection. In a sense, the Diamond Age is not just about technology. It's a story about how far human curiosity can go. From observing the stars, to understanding atomic structures, to mastering materials that mirror the cosmos. This journey illustrates a profound truth. Humanity is both a product of the universe and a shaper of it. Diamond is a perfect emblem of that duality. Born in stars, reborn in laboratories, destined to power the future. The Diamond Age is no longer a distant dream. It has begun.